Okay. So just want to mention that so this is so we will have for next week we have a class, and so this is the final 2 weeks. This one, there's a class here, and we'll have a midterm. Sorry, the final exam is December 19th, and yeah. And there's no extra homework. So I think we don't have like 6 homework. Right? 6. Okay. So this week we'll try to like finish the stabilizer through the common error correction. And by the way, so common error correction is like 1 semester in the United States. So it's like very heavy, very theory course. So but we only have like 1 or 2 lectures. Yeah. So so basically I will try to explain some detail, but not all of this. Okay, so just quickly recall, right? So remember that we first say about this show code, and we talked about so-called Pauli group. So Pauli group is basically the Pauli string, the standard Pauli string. So each qubit is either identity X, Y, and Z, and then some plus or minus 1 phase and plus or minus I. And the most important property of Pauli group is that even any 2 elements, either it's commutes or anti-commutes, because Pauli X, Y, and Z, there are anti-commutes. And if they are on the same sides, then they anti-commutes. If they are on different sides, they commutes. Okay, so Pauli group. And what we say is that we define a so-called stabilizer. So stabilizer, you can think it's basically some abelian subgroup of Pauli group. So yeah, definition. So definition is basically the abelian subgroup of the Pauli group, but you need to remove the minus identity. And once you have that, then you can define so-called cospace, or basically the cospace. So cospace is all the states which is stabilized by the stabilizer. So let me just write again. So you can define a set. Pn, which is stands for the stabilizer, and then you can define a cospace. We just all the NQB states such that stabilized by S, by all the element S. So that means that n psi or m. So basically, these are all the simultaneous eigenstates with eigenvalue 1 by the cospace. Okay, and once you have that, then you can define you can say some more about this error correction. Because what? Because if you have error, then so as we mentioned that since we have this measurement, right, so we can reduce all the error in terms of that. Basically, error is also elements in the Pauli. Like for example, if you have the bit flip, basically it's X error. If you have the phase flip, you have the error.
So the definitions for SD and the code space almost look a little bit cyclic, but this is because we are taking different states.
Actually, yeah, there are some technical details. You mean this one? Yeah, yeah. Actually, it's you have like two ways. So basically, if you're given a set S, then you can define a closed space, right? But conversely, if you give me any set, you give me any set. Let's say you get any okay, maybe it's for S. But let's say you take any subset of Hilbert space, then you can define a set which stands for like all stabilizers, all element inside a Pauli group, such that this m of psi equals to psi, all psi in X. So this is somehow like, so actually the precise definition of stabilizer states is that this definition needs to be compatible. So meaning that if I start with a stabilizer S, then I will define this code space, right? Here I define a code space of S.
Yeah.
And if I use this procedure, then I should get the same set. So that everything is consistent. You know, so
So we are using the same X.
yeah, basically. So meaning that these two are competitive. Because if this is the same as, I mean, you know some yeah. So if you start with a subset of poly group, you can define a state which is stabilized by poly. And then if you give me any subset of here versus a subset in some subset of states, then you can define the set of all the elements in poly group such that is stabilized by such that it satisfies this condition. So the consistent, actually the stabilizer states defined to be these two need to be consistent. So you need to make sure that S generate closed space, and if the closed space put into this definition, then you will get some set of S that need to be the same.
So they need to be the same, so that means that somehow my selection of M needs to be maximal.
Yeah, you can say that. Yeah.
So
It's similar in algebraic geometry, right? So it's like, for example, if I give you some of a lot of polynomials, then you can define a set to be you can define a root set, basically it's all the solution of that polynomial. But if I give you a set of points, then you can also define a set of polynomials such that all these points will be the roots of that polynomial. And then you need to make sure that you start from set, get a polynomial, give you a set, they need to be consistent. This is somehow like maximum here. So yeah, so the idea is that I mean I can view this arrow as a poly, it's also a poly the poly string. For example, if you have fifth fleet, you can start with X, and if you have a fifth fleet, it's basically Z. Oh, so I did it very simple because you have arrow, right? If arrow is a subset of poly string, then this arrow is either commute with stabilizer or anti-commute.
Yeah.
And but let's say if your arrow is anti-commute, EM equals minus ME equals minus EM, then if your error happens, then if you use your stabilizer to get measure, you get inverse, you get some minus. Right? So that means that if this happens, then I can detect. Error. Yeah, so this is the error detection. To detect error is very simple. If your error is anti-commute with any one of the stabilizer, then you can detect. Okay, so by definition, the undetectable error is defined to be what? This be defined to be all the error which commute with all the stabilizers. Then you are undetectable. But by definition, stabilizer commute itself. So actually, the undetectable error is defined to be, so this N of S is all the poly strings which commute with all stabilizer, but need to delete S itself.
Yeah.
Because stabilizer by itself commute with itself. Right. So this is the set of undetectable error. It is undetectable error. Yeah, so this is why design. Okay, so this is a definition of undetectable error. So basically, the undetectable error is basically non-trivial error from N of S delete S because you need to commute with all the stabilizer, but stabilizer commute itself. So you need to remove modulo this S. By definition. Oh, hopefully. Okay. So now we talk about correction. So knowing is that you have two ways. If you find an error, then you can send this message again. You can just I discard this transition. I just send it again. I don't need to correct the errors. I mean, it's not necessary. Right? If you find error, then I can just do it again. I don't need to do that correction. Okay, but if you want to do the corrections, then there's a more condition, because if I want to do the correction, I'm not just I need to know which error. You're right. So if I want to do the corrections, I need to know E. So I can redo this. I can do like E.
Yeah.
But if this is true, then I need to make sure that there's no two different errors. These to the same syndromes. So I need to make sure that E psi and F psi. Basically, you need this, right? At least, so it should be at least at least that one of n need to be different. It need to be. I need to make sure that. By the way, so the problem is on this. So I need to make sure that if this, I mean, if there is a if E and F, like two different error happens, then at least one syndrome need to distinguish them. Otherwise that F and E has all the same syndrome. Then I'm getting then there's no way that I can act different. Then there's no way I can distinguish. So actually this is a condition. So condition is that if I can say if a set of this is epsilon, and so this epsilon is set which is defined to be all the correctable errors, then the condition is that for any two difference error in this correctable error, this guy, I should say, this guy needs to satisfy this. Why? Maybe this is where this is in somewhat incorrect. First of all, if E dagger F is different from not in N of S. Because if E dagger F is in N of S, then this is basically say that E and F are indistinguishable from this syndrome, from all the stabilizers. Right. So if this is right, this one. If this condition is satisfied, that means that ME is the same as MF for everything, right? So it means that right, you can so if this condition is satisfied, that means that ME is the same as MF, right? For all.
Wait, doesn't it mean that M times E?
Yeah, you can say basically somehow like something
like M E dagger F is equal to E dagger F M. Right. Because that's the definition of MS. If an element is in there, it combines with M.
Yeah. So it should be.
Is equal to and then E dagger F M.
Let me see.
I thought that was good.
Yeah.
That's pretty.
But does this mean that? Let me see. Wait. So
Do we have any condition on E or F?
I think yeah. So I need to make sure that since we are talking about correctable errors, right? So this correctable error should be. Let me see. I know what you're saying. So this is the condition. This is the condition we want. Is it obvious? Okay, so
it's kind of the problem is that we have the same number of E and F on both sides of the equation, and
I think is it this? I mean, if this is equation true, this one is true. Because I can, let's say this is, if this is not true, then am I able to say that this guy is And times, let's say I start with here, but times F.
Yeah,
I
it
just
does work. If we can, if we know that E and F commute with the M, then it works.
Then it really works.
Then we can go and
Okay.
this is how the other way around.
With this one, right? This one. It's
Oh, then
yeah. Okay, let's see what you're saying. But I should. Yeah, I mean, I will try to find the answer. I will try to find it. I think yeah, I know. So that means that these directions, I mean, so these directions, so one direction is obvious, but another one is. Okay. Yeah, I will try to find it. When we talk about distance, which is the minimum weight of element. The minimum weight of element of Pauli weights in element S divided by mod S. Okay, so the definition, so usually for every direction we write NKD, N is the number of physical qubit, K is the qubit, is the distance. Okay. And so basically this results tell you that so this result tell you that if you correct up to T general errors, then we need to require that D equals to 2D plus 1. Because this use these results. This result. Because if you can correct these errors, then this is a condition. But let's say the set of because the minimum, because let's say if you can, let's say E and F are both like Pauli, the weight T Paulis, then an E dagger F is at most the 2T weights Paulis. Right? Because let's say E, there is some weight here. So this is T weights, and then these are T weights. So E dagger F is at most 2T weight Paulis. And but minimum of these guys, let's say minimum of these guys is D. So if D is higher than a 2T plus 1, then definitely is condition satisfied. So that means that if D is higher, then you can correct more errors. Because the minimum element inside these guys weight is very high. Its weight is very high. So definitely you are not, if your D is higher than 2T, basically 2T plus 1, then basically this condition will obviously satisfy. Okay. And we talk about some codes like 513. I can check it. If you want to know detail, you can just go to the error correction code. As I said, you can just go online, find on the error correction. And yeah, these are like done by hundreds of people. So many people. Yes, basically I think the founder, know that this is the founder. Actually, I know him personally. Like 2 years ago. And there's the show code and okay, so and we say that so basically this Pauli error correction idea is that you have these NKD codes. So if you have some errors, then if your error is no way Pauli, then you can use this error correction to correct it. So in this 2EC sense, it's basically imagine that it's a gate is perfect or there's no so this you can view this is 2EC somehow if you want to store quantum information or you just want to send a quantum information. But if you are trying to do a quantum computation, then you will run some extra problems. And the idea and the reason, as I said, because if you want to do a quantum information or quantum computation, then you will have some gates which use like 2-qubit gates. For example, this CNOT gate. Okay. And the idea basically goes like this. For example, if you start with 0, 0, and then you have some arrows, maybe your control field has the arrow become 1. And if you apply CNOT, then you get to 1. Right? Because this is control, right? If your control become 1, then you will be acting on your target will get 3. So that means that even gate is perfect. If you apply the CNOT, then 1 qubit, 1 arrow will become 2 arrows. And you keep doing, then you get a lot of arrows. And yeah, this is more interesting. This is more interesting scenario is that for this phase split, this phase arrow, if your target has an arrow, for example, 0 plus 1 becomes 0 minus 1, then actually this phase arrow will propagate backwards to the target. So it becomes 0 minus 0 minus. So the left one, so this right one scenario is never happened in class. Because in classical, basically control, if your control is wrong, then basically target will. Right? But in this case, is that if target is wrong, then control will. Okay, so this will be the problem. And if this problem happens, then quantum error correction will have the trouble. Because, for example, if I take my 713 code, I have 7 qubits, and I can correct any 1 qubit errors. But if I do some CNOT here, then maybe my errors, I have 2 errors, and quantum error correction fails. Right, okay. So, yeah, this is what previous said. So 713 code is what I use as an example. So in order to do this CNOT scenario, what people find for the 9 ways using so-called transversal gates. For example, if I want to do a CNOT on 2 qubit, right? So now these 7 physical qubit only encode 1 logical qubit. And then if I apply CNOT transversal, I apply CNOT here. And if there's a 1 arrow here, then even arrow propagate to here is fine because if these 7 only have 1 arrow. So I get to okay. So this is so if you in terms of plots, just definition of transversal gate is just 7 of them, and you do all CNOT. And if these are arrow, one happen, then you can correct. And then notice that the definition of transversal is that only 1 pair by 1. So I mean you are not allowed to like 1 pair. In 1 pair, because the reason is that as I say that in quantum information that phase flip will get backwards. Right. So if you have this guy, maybe if you have two line, and they are all controlled the same qubits. If there is an arrow happen here, then this arrow will propagate to the above. So then there is a problem. Okay. So and similarly that you can do the transversal you can do basically this is Hadamard and CNOT. So what I want to say is that you can do all the Hadamard gates, you can do a CNOT gate transversal. Single qubit is simple. Single qubit you just do this. Do as a previous what you did. So you can do some logical Hadamard, just apply 7 Hadamard, and you can apply logical CNOT, just 7 CNOT as this plot. And you can also do R pi over 4. Okay. So now if you are convinced by me, then we're doing a logical Hadamard, logical CNOT, logical pi over 4. So the question is that universal, right? In terms of quantum computation that you need to remember that we prove some results that if you want to do you can either do single qubit plus CNOT, or you can do some Hadamard CNOT and also the so-called T gates. Is that universal? So this is the question. Okay. So however, there's a Canino-Gottesman theorem say that Hadamard base gate and control CNOT gates. If you only have these three gates, three gates, then your results will be if you start with the state which are eigenstate Pauli, and then you also measure in a computational basis, then this distribution is classically similar. So what is Gauss-Lagrange theorem say that Hadamard phase gate and CNOT gates, they are not universe. And basically the reason is that part of the reason actually the reason is that they are all unitary which stabilize the Pauli group. So it's like U dagger equals to Q. That means that if you start with any Pauli, then this conjugate by these elements, there must be another Pauli. So that means that this unitary has some particular restriction. And as I said, that Hadamard, CNOT, and R pi over 4 satisfy this condition. Okay. Okay. So now the question become like, so the now story, like is there the other like quantum interaction codes that the universal like transversal gates, or at least so-called outside the Clifford group? And answer is no. No prior I know that linear symmetry X transversal of physical group. So that means that you are not allowed to do quantum computation using this transversal method. Okay, so this is the story ended last time. Okay, so how to do with it? So this somehow like answer is complicated. Yeah, I need to. If you don't want to know detail, it's very difficult. But I try to like do quite. Okay. So, right. So remember that this Clifford gate plus another pi with 8 or people call it T gates is basically universal. So meaning that the remaining is that if you can do this gate, then you are able to do a whole quantum computation. So the remaining is just one gate. But this gate is not like cannot transversal, right? So we need to do this so-called R pi over 4 basically T gates using quantum error correctness. So what? Okay, so people like invented a smart way basically called magic state detection by Titov. Okay, so let me just explain what's the magic state. Let me just quickly say about this. Okay, so if this is the first time you learn about it, then yeah, I will. So the thing is that I want to do T gates, right? So T gates that's 1 0 0 0. Like 4. Notice that when this is S, if it's I pi so it's S gate, then S gate is complete over. Okay, so we need to do T gates. Now imagine that for some reason, someone handing you a state like this, T applied plus. I mean, this is not what you do in experiments. You are not really do T applied plus. Let's say suppose someone give you a state, handing you a state like this. Someone inject this so-called magic state. So it's X. I give you some magic state. This is magic state here. And the claim is that there's a way to implement T gates if someone gives you this state. Okay, so this is the so-called magic state. Okay, so let me explain the idea. So if let's say we do single qubit, and I start with single qubit side, and I do T, and there's a T plus here. This is someone gives you. I'm not able to do T, but let's say someone gives me this magic state, and I do this control this CNOT, and I do measurement. Okay, so let's say let me just do a math. So this magnitude is T plus tensor psi. If I do CNOT, then it becomes probably 100%. So let me just do the. So this is if this is the first time I realized you will become like very, very big. Right, so this is T. And remember that T is 1 over square root 2, like 0, plus is going to I pi divided by 4. So, here. And tensor with some, let's say, some state, right? So, so alpha, let's say alpha 0 plus beta 1. Okay, so let's say we do this computation. And now I connect 0 here. So I connect 1 over 0 here. And 1 again. Well, so no, so this is the this guy right here. Right. Now let's say I apply C naught. C naught. So if this is a 0, then there's no fit. If there's a 1, there you add extra x here, right? So it becomes like 1 over square root of 2, 0 plus. If it's 0, then there's not there's the remaining of same. If we would let me just maybe I expand it. Or I expand it using. So when does so notice that you see now is there. So if this is 0, then you apply nothing to the first thing to this thing. And if this is 1, then you apply extra x here. So you flip 1 and 0. Right, so it becomes here. 0 and beta. Good. C naught. So you start with this guy, then you apply C naught down here. Because when this is 0, then you apply nothing to the first. If this is 1, you apply extra x. You flip 1 and 0. Okay, so now if you connect it back, right? So you connect 0, you connect the first step 0, then the remaining state will be 1 over square root of 2 alpha 0 plus this guy, right? So it's 1 over square root of 2 equal to I divided by 4. Okay. If this is 0, then 0 is beta 1. Okay, and plus if this is 1, if you collect the term which the first is 1, then you get 1. 1 over square root 2 is equal to I pi divided by 4. 1. Then 1 here. Then alpha. So we collect the term 1 here. So we get 1 over square root 2 beta. This is 0. Okay, so what you say is that the first state is 0, the second state here, that alpha 0 plus exponential I pi divided by 4 beta. So this is basically the t acting on the state side. And this one, if you take out some phase, then you get these results that 1 plus I divided by 2, 1 over t degrees. So you can see there's a, so this is clear, right? So this means that if I do a C naught, then somehow like this t, then action of t is teleportation to this state side. The original acting on the plus, right? So we get this. Oh, so now idea is very simple to measurement of the second thing. If it's 0, then the remaining will be t acting outside in 1 volt. And then if it's 1, then you just apply something to get this thing. So yeah, so if the second outcome is 0, then you do nothing. You get the output state inside. And if the outcome is 1, then you can just perform another S case. Then you can see that S dagger, because T is somehow like half of so S is somehow like T squared. So you get T side. So what I want to say is that I can use this idea so that I can apply. I originally want to apply T acting on side. But now this procedure tells me that I only need a state, which is called T box. I don't need to implement TK, but if I have a state which is called T box, then I can able to use this procedure. Because I can do C naught for the person. So this is why T is this T plus is called magic state. I mean it's not unique one. So but yeah, so the general textbook using this as okay, so the idea is that if someone gives me this T plus, this magic state, then I can do whatever. Then I can do the quantum. Then I can able to like hopefully pass this T. Okay, so now if I have the Clifford gates, like this all these Clifford gates and plus this magic states, then I can do like I can do the quantum computation. Okay, but now there is another problem. I mean, how can one produce this T plus? Let's say so this protocol tells me that if you give me T plus, then I'm able to do the computation. And probably a big question. So we don't have an answer. You can check out the depth and basically it's called magic state stimulation. So somehow you have a certain procedure that you are able to get T plus. You're not basically solve plus by T. I mean you can do this, but the states you don't have enough data for your T plus. But there's a way of this stimulation that you can get the theoretical, you can get the high fidelity T plus. If you keep doing this stimulation procedure. Yeah, so the details are complicated. Hard to say. Thanks. It's beyond this course. Okay. Okay, so so imagine now you can do Clifford gates, and you have this T plus, you have this very clean T plus, then next that now you can do a 4-time computation. And there is a theorem about it. So let me just tell you the idea. So remember that in the very beginning, in this repetition code, I say that if you start with 0, and you can just in advance we can do this review. But in content you have this error correction. Okay, but this is the proof idea is similar because originally that if you have single qubit error with probability P, and then if you build some error correction codes, then you can correct, and if these error correction codes are able to correct any single qubit error, then basically so single P, then you can then the error probability start with P and shrinking to like maybe like some P squared, CP squared. Because if you for example, if you use this 713 code, and now you are able to correct any single qubit error. So the procedure, the failure procedure decrease from start from p to some constant times p. Because single qubit you are able to do, right? But now becomes CP squared. For some C. So C is basically on the geometry of different error correction, but C is a constant. Okay, so let me just give you a feeling why you can use this. Because let's say I start with that 713 is hard to write. So let me just using the 3 x repetition code as an example. So if we start with 1 qubit, now we use this file, we use 3 extra qubits. Physical qubits to encode this one logical qubits. Now your error rates become p to CP squared. Now if you can do it again. You can use another 3 qubits, physical qubits to this qubit. So you do second.
Then also your encoding needs to be.
Yeah. So you have 9 qubits. Right? This is problem. Right? So but let's say now you can see it. You start with p, right? Then you got CP squared. If I use extra 3 and 3 times qubits, so 3 times qubits, then this p will become CP squared. If I do it, that becomes CP squared. So the idea is that you can see that the arrow actually you start with 1 and the 2, and it is 4.
Isn't there one maybe in the fact that we do first need to make the longer logical qubit? So maybe there's already a mistake when we are converting our one physical qubit to a lot of physical qubits.
Right. So we did. I mean theoretically, so if you do an experiment, yeah, there's a problem. So
Yeah.
I mean theoretically it's right. Let me just. Yeah, I mean in the experiments, people need to make sure that if you increase the size, then indeed that you will get more extra errors come from this larger system. So this is the problem that people try to make sure that this is let me see in the experiment. So the idea is that theoretically you start from here, right? Start from there. Now you go CP squared. Now you can see that this is whatever, but this is P before. But now what you want P. Now you can just concatenate. You can just so. So maybe I use this one. So let's say I write C as a 1 over P. I use for the convenience. Maybe here. Right. So at the beginning, that you get P. So the first layer is P, right? The second layer is like somehow like P squared divided by the PT. I write C as 1 over PT. Okay. Now if I do it again, I get like P root force. P root force. I get so this is the second layer. I got P. Second layer is P squared divided by PT. Okay. Now you can do a third layer. You get P root 4 divided by PT. And you can just keep going. So but the idea is that this is the result. You can see that you need to do a computation, but the error basically goes extra. p divided by t to 2 to the k. Because it's obvious you want to replace p to be p. So if you do the layers, then you are 2 to the k. But what I'm saying is that so these arrows, indeed, if let's say if your p is less than pt, then this is these terms. It's basically double exponential of this. Okay. Because this is exponential, it is exponential. But now you have like 1 or 2 there. So this is 1 exponential. And this is 2 exponential. So that means that if you compare k layers, then your arrow actually decrease double exponential. But you only increase your cubic exponentially. So there are 2 extra exponential factors. 2 extra exponential factors. So this is the idea that basically what this theorem says that if there is some threshold, the threshold is pt based on different error correction codes, and arbitrary long quantum computation are possible. The reason is that I can do the k labels concatenation of these error correction codes. And I know that error will goes down double exponential. Then I just pay a single exponential number of qubits. So if I want to do like quantum computation for length t, for some t gates, first gate, second gate, up to the main t gates, then I only need to do like log of t labels of computation. Because error decrease double exponential. So I need the log of t gate. And I require like polylog t extra qubits. So that means that if you have an algorithm that you need a lot of very long quantum computation, you only pay. You're not pay a lot, but you just pay an extra polylog t.
Yeah. So
that you can make these error arbitraries. So theoretically, once you have this whole tolerant quantum, this whole mathematical framework, and then you just keep using this. You just keep using this fault tolerant, this error correction code to keep encoding, then the error will quickly goes down. So this is why people, before this fault tolerant quantum computation, this framework, that people will argue that quantum computation is impossible because the physical error rate is very high, that you are not able to do like any very long computation. Maybe you can do like 3 layers. But if you want to do Shor's algorithm, right, you need to do thousands of different qubits. But after this theorem or this whole lot of quantum error correction story, then using this double exponential all these quantum error correction codes, then it makes the quantum computing that looks possible. Okay, so this is the story. So I did that you need to do a single qubit CNOT, and you can do it in quantum computation. But if you want to use this fault tolerant, use this fault tolerant, in order to make this decreasing, that your p need to be less than pt. So there will be some threshold that you need to your physical error rate need to bypass. It need to be smaller enough, smaller than this threshold, and you are able to using this theorem to keep going. And if I know, this is all the number that I know, but so you need to do that for either 2 qubit or single qubit fidelity, you need to be very, very high. And if 30 years ago, there's one type of error correction code that requires the 2 qubit fidelity need to be like 6.9 after the 0.9. And previously, experimental belief this is somehow like impossible. But after 20 years, I think now the 2 qubit gates. That's one of my friends there experimental that do like 0.9994. So it's very, very close. 0.99. Now it's 0.99 and target is 0.9999. So what theory believes is that if you're 2 qubit fidelity bypass this limit, then you can use whole previous procedure that you can go on. And these are like two two different paths. One path is that when people try to find a better corner error correction codes, such that this PT can be increased. If you want to write more theoretical tool, then you can increase this threshold. And experimental people need to like try to make the logical physical errors smaller, so that they can match this. And once they match this, then you can do this whole quantum computation.
So isn't this, so somehow if they are using codes for the correction and the PT is dependent on P?
Oh no, the PD depends on the error correction code itself. For example, 713, sort of a family of error correction codes.
But is the C that is given here the initial P or?
No, C is independent. So for I mean, remember that for example, in this classical repetition code,
Yes.
C is the constant that you reach.
Okay.
And
So,
C is constant, some constant, based on your code, based on family of codes.
yeah, okay, so C is equal to
C
1 over
is-
PT.
Yeah, some number. So you once you define a family of codes, then you get some C. You get some threshold. It's not. I mean, it's the typical is to be 0.01. It's very small. So once you define, and then you need to make sure that your experimental match can beat this. And if you can beat it, you can run this whole procedure. Then you have the long quantum computation. So this is why people like, I mean, past 20 years that people try to do that. 10 years people try to do the error correction.
So why is it so high? Because 0.99 is quite high.
Yeah, but I mean, there's so yeah, because we are, I mean, previously I do this repetition code, so this one is, but
Yeah,
But-
it's like very low actually.
yeah, but
Wait,
indeed that, yeah, so I will basically talk about some other codes, and you will say, and yeah, for some reasons that this, yeah, I mean, I don't know what's the state on this, but the experimental up to now, there's a people using so-called service code, and I think this service code has.
We need to consider the error of the between manufacturer will take the semantic constant that depending on the hardware architecture.
Yeah,
That's why different papers they will need to mention which decoder.
Yeah, so basically there are some technical thing on this. So yeah, basically these are dependent on your code. And also hardware. So this PD is indeed in general is very small. It's up to now, I mean, there are maybe some like much more like mathematical codes that which can have higher enough PT, but these guys are not able to do that.
Yeah.
So that what people believe now is what people try to do is so-called service code as like 0.01 or 1.001, and not very high. Right. So yeah. So this is the I want to talk about service code. So basically, maybe you heard about so up to now I think you believe that it's basically this quantum error code is like some area which a lot of advanced mathematics. And indeed very this yeah so I will talk about some other like Abalian codes, but yeah, it's like fourth semester. I mean you can just go YouTube and find the error corrections, and there is videos that you can check. One 1 hour, like 10 hours of different videos. Okay, these are something. Oh, by the way, you can just if you want to know more, then you can find the parameters on the correction. You can, if you want to know all the details, then you can check out this one semester course. Very handy. Okay, so these are 713, these 513 are small codes. They are not able to do like very large because yeah, this is just some toy model. So in the real experiments, that people need to develop the scalable quantum computation. So they need to use the better codes. Okay, so
Wait, because if didn't you show on the slide that C was about 0.99?
no.
Because that would make no sense.
Oh,
Because then C is
no,
just bigger than.
that C is different from this.
It's a difference.
Yeah, it's a difference.
Because otherwise it makes no
Yeah,
sense.
yeah, yeah. So that's the just. I just want to say that. I mean,
Okay.
so three people like try to like find actually this I mean people like try to find a code which can scalable and that can be done in the experiment. Oh, and this is for service code. Actually, there are a lot of it, but let me just talk one example. If you, this is how much more condensed later, but I will try to explain it and I mean you can if you want to know more, you can check out other online reports. It is somehow very different. Okay. Okay, because I mean, if you want to do a scalable quantum computation, you need to consider a physical qubit. So, and I mean, in physics, there's a somehow like the natural constraint that one particle will be if you have two particles they are if you have two particles they are close, then interaction. So your interaction will be higher than the very far qubit. Right? So that means that this interaction are local. So somehow like if you want to build scalable, then this qubit should look like planar or something. So the standard planar way is using so-called Tori code. So you can understand this Tori code using stabilizer formalism. So now I mean if this is the first values, maybe you would see. So now you imagine there is a square lattice. And each qubit is placed on the edge. So each edge has a qubit. Okay. So maybe I plot. This is somewhat much more condensed method, but hopefully I give you some idea. So you have a square lattice, and each qubit is on the edge. No, this is different from Ising model, right? The Ising model that is on the edge. It's on the vertex, but now this is on the edge. Okay, now I can define a stabilizer, right? So remember, a stabilizer is a Pauli string, right? The set of Pauli string. So if for vertices, this is called vertex. It's defined to be using x for x. So one stabilizer, maybe I use this. And then you don't need to care about Hamiltonian, but you can see this. Maybe this. So it is penalty. So for these vertices, I should use for x, x1, x2, x3, x4. These 4x are the stabilizer. Okay. Why? That's definition. Yeah, I will talk about this is the definition. I will say the reason. So this is x, 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 x. So each vertices has an x stabilizer for x. Okay. And each this is called packets. This P has 4 different z as a stabilizer. Okay, z.
Like the other way around from the picture.
This is not. Maybe so maybe use
Okay.
That's the other route. This for the company. That's fine. Okay, so you can see that the idea is that these are commuting stabilizer. It's not obvious, but you can see that if you have x, right? You have x, 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 and you have z in this packet. Actually, they are commutes because there are this x and t and that commutes. This x and t are and that commutes. So this packet and this star are commutes, right? X, 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 z, they are commutes. Because these guys in that commute, these guys in that commute, and each packet and star, they touch even number of edges.
Good. Wait, so how actually do we define the operations and all and convert it into mathematics?
Oh, mathematics just for each vertex, the stabilizer just x, apply on these 4 qubits. And for this packet, the operation is d on these 4 qubits. So once you fix the lattice, then all these stabilizers are defined. For each vertex, there are 4x. For each packet, there are 4z.
Okay, so the C and the X anti-commute.
Yeah, so these
Yeah.
anti-commute, these anti-commute, so these bracket anti-commutes with this four.
Because for the other ones, we don't consider them. Because they are not acting on the same period.
For example, this one, there are commutes. Right, because they don't act on the same period, their identity, their rest are.
Okay, yes.
So for this one also, this one and also this one.
Because they're orthogonal.
Yeah.
Okay,
So
yeah.
so that means for in terms of condensed matter, we have Hamiltonian, which you sum over all the vertices and sum over all the pockets. So basically, what I'm saying is that the code space, right? The code space is defined to be the plus one eigenstates of all these operators. And can you imagine that what wave function looks like? This is very, yeah. So the wave function, there are some wave function, which are like simultaneous eigenstates of all these operators. And it's very, you should imagine that it's become very entangled, very complex. Yeah. So the idea is that if you do the error correction, then you don't need to know what's the shape of this wave function. But I can maybe tell you something. But okay, so notice that this wave function will not have definitely spin on any one of the edges. For example, if this wave function has some particular spin up on its edges, then it will not be fixed by, it will not be the eigenstate of this x, because once you apply x on these vertices, then this get flipped.
Yes, yeah. Because if you apply X on vertex, then it's going to flip.
Yeah. So
rounded.
but mathematically, there's a some wave function because all these are commutes. So there must be some wave function which is the eigenstate of all these operators. And then my idea is that can you imagine what this looks like?
Wait, is it something you can calculate for a simple one?
You can understand the structure, but if you want to write everything down, but we at least know something about this.
But like for a small one, if you only have one.
Yeah, for little one fine, but
Only one.
but no, imagine that I need to spend a whole power computing. So it's L should be like larger and larger. Can you imagine that that's the way function looks like? Okay, so let me if you let's try to let's see. Yeah, let me just try it. Okay, so this is let me just talk about some property. So the vertex and bucket are commutes. So I know that since they're all net, right? So they are co-commutes. So there is a ground state must satisfy all the vertex and bucket terms need to be one. Need to be one.
Eigenvalue.
Yeah, eigenvalue. So then, so let me let's see. I just want to try to write. Imagine I try to write the wave function of this. Try to. So let me just tell you. So let me see how should I explain this wave. Maybe let me first talk about stabilizer and then we go back to this way. So in the real, if you want to usually in terms of condensed matter, if you want to understand, they will put this surface code on the torus. So on torus meaning that you will identify these edges as this edge, as the edge. So you can imagine that this is Because you imagine this look like this.
So it's surface.
Yeah, this is why people go surface. Imagine that. So now become xx.
Do they do this for symmetry somehow?
The reason will be clear. So the idea basically looks like this. So if you right, so if you put it on torus, then let me maybe see here. Maybe see here. So if I have the negative side, let's say L plus 1 times L plus 1, then since I identify, so total will be you have 2L squared cubed. Maybe it's hard. I mean, if you can see 3 of if I do that 3 times 3, then here. But since I identify the number the edges, so that means that these 3 are the same as this one. So I do this. And oh yeah, around 2. Here. Yeah, it's 3 times 2. Around 2. I forget about that. But remember that, so the cubic on edge. Right now, if I identify if I identify this with this, and then there's again this about this. And 1, 2, 3, 4, 5, 6, 7, 8. So it's 2L squared. Now L squared. Okay, so you have 2L squared qubits. And how many constraints you have? How many constraints? So each you have else, you can maybe see these problems. You have else, you will have L squared stars. Stars basically XX, then you have L squared plaquette. So total you have like, because each plaquette will give you one constraint, 1, 1, 1, 1, and the star you have 1, 1, 1, 1. You have some 4 star and 4 plaquette. So total you get like 2L squared constraint. So you might think that there's unique ground state because now you have 2L squared qubit, but you have 2L squared constraint. It looks like you have unique ground state. But they are not actually independent because if you times all the vertices, you have all the plaquettes. If you times all these plaquette term, then you always get 1. Because let's say each plaquette is z. So if I times all these z, then each vertices will touch by 2z. Right? Z. And also each vertices will each plaquette will each edge will touch by 2z, and each also this x. For example, if I do x here and do x here, then I will get touch. So there are actually 2 global constraints, which is trivial, or it's much trivial setting. So that means that you only have like 2L squared minus 2 independent stabilizers. So it's a 4 minus 4.
And so here the multiplication is the tensor product for the A.
Yeah, indeed. So that means that you have 2L squared dependent variable. Okay, so now you have like 2L squared, but only have 2L squared minus 2 dependent variables. So you can get like 2 logical qubits. I mean, for the torus, you get 2. Right? If you put on planar, then it's so you get 2 square logical qubits. 2 square, 2 logical qubits. Okay, so even though you are not going to like understand how to understand the wave function, but this code indeed gives you 2L squared 2. Right, this 2 elsewhere is number of total qubits. And the 2 is the constraint. This is the one I say that you get 2 elsewhere minus. So 2 is the number of qubits. And the idea is that this L distance is large. This is distance indeed L. So this is I mean, okay, I can try to explain why this is why these topological codes are like somehow like robust. Right, so imagine that you are in a code space, that you are already in the code space. So now you have the states which are very complicated. I mean I can try to explain, but let's say you imagine there's this very complicated state that you're already in this, and then you have let's say you have some error x here.
Yes.
Then it's able trivial to detect because this guy this d will detect. D will detect because this d will give you a minus. But this d operator will say, oh, this is a single minus. It will detect. And so okay. So obviously that it looks good. So you can see that there are maybe and the more difficult one you can also detect. For example, this one. I mean, if you have error like this, you have x, then this z will detect d, and this, and you can see, oh, this one may not detect because there are two extra x. Oh, sorry, yeah, this one.
That one will detect. Actually.
Yeah. So what I will say is that you can see that this is like very strong. Because yeah, if you're so, but there's a thing you might not detect. For example, you can for example like this. In this one, you might not detect. You are not able to detect. You now imagine that these are closed functions. They are periodic. So
yes,
these are +1.
Yeah,
these are +1. These are +1. And these are connected together. So if you have x, then you are not able to see that. So the idea basically say that I'm not the proof is not coming, but the idea is that as long as your arrow is not cross this, then you are able to detect.
yes. So why can't we also do the Z test on a vertex instead of?
Oh no, the definition Z is on the bucket, and the X is on the vertices. If you do that, then you are not able to get the commuting. Okay. You are not able to get it stabilized.
Okay.
Right. So
because otherwise we could detect it.
right. So the idea is that so you can see that. I mean, you can see that if there's no error here, then this one will be able to detect. So that means that this somehow like this service will have no solo plus. That if you have error like 10,000, right, very large, then as long as your error are past very large, you need to have very large long error so that this you will not detect. But if your errors are very local, the length is not so. If your arrow is not cross this boundary, then you are able to detect. Oh, by the way, in terms of phase arrow, then basically is yeah. Or I mean another way that you're not able to detect this the because now if you have Z, then this X will touch twice. You're not able to detect, you're not able to detect. But these are just so as long as your arrow does not pass this, then you're able to detect. So that means that if I can make very large L, then I can make this very large. In general, I can do this will be very robust. Yeah, for very large L. So I can use this to encode the very large, very robust error correction code. And it's just scalable, meaning that I can keep increasing. It's not a single family of codes, but it's not a single error correction code, but a family of error correction codes by different L.
Yes. Can you maybe calculate the wave function for L as one?
I mean, small L, one can do. But I mean, I can explain I can try to give you the, okay, let me just tell you the results. So the results basically, say that for the ground state, the wave function is a superposition of all loops configuration. Let me explain what is mean. I can, oh, sorry, I write. Okay. So if you start from this way, if you start from the so okay, so let's say hopefully I can convince you. So my claim is about my claim is that this wave function size or is some very large superposition. So of all the loops configuration. So that means that I start with all the vacuum. So vacuum means that all, I mean, let's say every spin are down or something. Let's say every spin on every spin are on all zero. But this will not be the wave function because as I said that if I apply x, then everything will get fit. So, but now I can do like one loop, meaning that I can do this. So this meaning that I apply, let's say I apply x here. Now I can do another loop. Maybe here I get x.
Because this wave function should
be stable
with all the possible operations.
Yeah. So okay, you know these two. So this wave function indeed is very complicated. I mean, so mathematically one can prove this. So now I mean, I can prove why. So first, if I apply any x terms, for example, I apply x term here, I will flip this force spin. But since I already consider all loop configuration, so I mean, so this flip will inside it.
Yeah.
And moreover, why you can show that this must be a closed loop because if you have some open loop, let's say you start with you start here, so you have some open loop as you apply x here, then this will not be the wave function because now this one will have a problem. So in order to have all the one eigenstates, then you need to make sure that this loop must be closed.
Yeah.
So all these closed. So the first thing that so to prove this, the first one is that I know that first I need to close loop. That's why, because if I have a closed loop, then all z are this product of z are this Plaqueta loop. So loop meaning that if I flip this spin, then for each spin configuration need to be the plus one eigenstates. Then of product of z, it must be closed loop. And once you have the first statement, then but you know that this wave function must also be fixed by every x. So makes the ground state to be all loop configuration, dimensional all loop configuration. So my answer to you is that indeed, if you give me any L, then L is 1 or 10, then I know that the ground state must look like this. Ground state are all the superposition of different loops. So these are very highly entangled objects. You can imagine that there are so I don't know how to count the number of loops.
Yeah.
Here, but yeah.
I guess L is one is a little bit strange because then you really only have.
Yeah. For since small L is fine. Yeah, but you can imagine that this is
Yeah.
So this is why this is called topological. So these things are very highly entangled, and they are robust. Yeah, by definition, because as I say, if any single qubit or any small local errors, then all these very dense like object that you can detect.
So wait, so what would it be for LS1? Because if LS1, then
Oh, you
we
have-
don't really have,
Yeah, you don't have anything.
we don't have a plane, and
Yeah,
we don't have.
You don't have any qubit, yeah. So because for L equals to 1, no, because now you're already connected it. So I think maybe it's well defined, only well defined L greater equal to or something. Okay, so 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 this is so-called service code. You can find more that. And there are other kind of codes. We'll try to explain it. Oh, by the way, this is much more better feature. Okay. So this is in the service code, you identify this. Then for this guy, for this bracket, you use Z. Then for this vertex, you use XX.
Yeah.
So there are very complicated ground states, and they are very robust because each small local errors can be detected. Easy. Okay, so we take 10 minutes break.
Yeah.
Okay, well, maybe this figure is better than what so this function is the product of D and stabilizer is X. So I mean these are just some tutorials of that you are better feeding better. Okay. So then so I'm actually I just use it. So they are confused because they only touch given number of sites. And for detecting errors, let's say these edges are detected. By the way, there are some you can see a reference. I just post a reference in this thing. These are not done by me, but I will be found. So if there's a red arrow, but if the X are here, then these two blockades will detect. So detect errors are simple. And even though you have long errors, let's say these are X here, then this arrow and these two blockades will detect. So then you can run like different decoding algorithms. You can just try you can just try if you have to use these two, then you can use a minimum width decoder. So then you try to find a minimum X from here to here. Maybe so you still get some errors, but the detection is very simple. But if you want to do the correction, then you need to write something else. Because you get two, right? You need to see maybe there's two extra paths, a lot of paths that give these things sense,
So in this case, if you make a circle, then wait, that's the next thing.
Yeah, I mean, if your errors are loops, let's say your error are X, then this is nothing. Because by definition, then your loops become a stabilizer. So your error must be open-ended object. If it's closed-ended, then you're already captured by this.
Because if it is closer, then
There's a certain
actually
you cannot think. Yeah. So you cannot, so you don't need to worry. Okay, so this picture say that maybe you can see there are two extra paths. Maybe so now you have yellow path or the red path. These two give you a sense interval. So so if you correct errors, you need to write some other algorithms. But mathematically, let's say each qubit has a same probability flip, then I would able to believe that probability that yellow happens is greater than the probability that red happens. Because the red has more Pauli weight. Okay. So this is the idea. Okay, so so these are all out the same. So the final the final things to just try to tell you that how one can measure. Okay, so when we do like error correction on two extent, so it's very simple that I can just write that I'll measure x here on the. But actually, one can do this using quantum circuit. Oh, so these are just some small details, just tell you that how people measure in the experiment, how people really measure is z, or x. Or for example, if I want to measure the x1, x2, x3, x4 on either maybe any vertices, then what I can do is that I just remember I have 1, 2, 3, 4 like this. Then very simple, I C naught here, C naught here, C naught here, C naught here, and I prepare this to be 0. Right. So this is 1 qubit, 2 qubits, 3 qubit, 4 qubit, and these are so-called theta, which is a qubit that you need to prepare. You prepare on 0 state, and since you C naught fall on this, right? So this guy will be x1, x2, x3. Because if x1 happens, then the basically if this is 1, then this x1 is 1, and if this is flip, then you get x2, x3. So you can use this simple form of C naught to measure the product of x. So if you want to do an experiment, then this, for example, if I want to measure x here, I need to put another NCR to be here. So that if I want to measure, let's say, so if I want to measure x here, I need to put extra NCR to be here, so that I can run this circuit. So I can do C naught on this, C naught on this, C naught on this, and I can get x. I can get 4x, then I can measure it. And then if I measure it here, and if I get 0, that means that this is +1. If I get 1, then this is -1. And similarly, for z, z is similar, but you need to do reverse. You get plus states and use the C naught is on another. But yeah, you just change your basis from using Kalman, change your basis, then get z. Okay, so this is what. So you can imagine that it is very heavy. Okay. And yeah, this is a service code. And sometimes then people will use another open-ended service code, similar as original service code, but just has some boundaries. Because sometimes then you can cut this boundary, but it's the same. If you have at the boundary, if you have open-ended the boundary, then this stabilize, then this you just follow this rule. For example, the vertices on the boundary just do x, just do 1x. And for z, just do this, z. And you can see that they're all still open. So this is not important, just some small, and sometimes then you will see this, you will see some paper, but some people will use this picture. So what this picture is basically say that it's just basically the same as service code, but they do a rotation. So they put qubits on the vertex. So they put qubit on this vertex, and they use black and white to distinguish different stabilizers. For example, black denotes X stabilizer. So you measure x here, and then white as a z stabilizer. So it's z here. And as you can see, similarly, these two are done by x, these two are done by z. So whatever they touch, they always touch even numbers. So they always. So this is not important. It's just a picture that if you see some papers, they will write you see black and white. It's the same as service code. Okay, and there are much more like interesting other kind of counteraction codes. You can just find in quantum version 2. For example, one is called like color code. But let's say color. So let's say remember there's a spin codes or 7 qubits. You can these are all stabilized 1, 2, 3, 4, 5, 6, 7, and you can put this as a 2-dimensional triangle. Let's say. And try to make sure that for example DZ they will touch by these 4 rings. Because it looks like some small cube picture. You can try to put this out. And then why this is called color code? Because this graph is 3 color code. 3 color code meaning that you can try to put this in using different colors. And using 3 colors such that each different neighbor, if there are neighbor, they have to be different colors. For example, these are some error correction codes. So there are 19. There are 19 qubits, and you can put it. Yeah. So basically, this is the so now you can see there are 6 in here and 6x here, and they are commutes. It's hard to see there. So so this is just funny thing, and also this let me just talk about. So this for actually one can also generate these Fourier codes into so-called these color codes by changing these square lattice to hexagon. So these are just some funny things. But I mean I try to. I just want to tell you that error correction in the deep south probably is so deep. Yeah. You can do a hexagon. And this hexagon somehow 3 colorable. For example, you can color this by A, you color this by B, and you can color by C, and this one must be B, right? This must be A and B and A and C and A. And you can define your stabilizer to be. So now let's say QB is also on the edges. So stabilizer has you can put basically each edges. So sorry, each edges you can do, so this guy you can stabilize as x. There is 6 of it. 6, and then you can put also z. So you can see that they are all commute because if these are all x, then let's just do this. X here. And if you do all z, they touch with 2. Right? Oh, by the way, there's a. Sorry. It should be on the vertex.
Because it should work for 1.
Yeah, this one. You can do like easy or something. So
and you can do that right because then they will hit 2.
Yeah. So what I'm saying is that you can just generalize this into the hexagon, and you can get this type of so-called color codes. So I mean, there are a lot of different error corrections, but to be honest, the real thing about it. So notice that in this service code, they are only using at most 4-way powers because you're either for X or for Z. So in an experimental, there's some reason that people cannot do that very high weight poly measure. You cannot do like 10x measurement. This is experimental difficult. So they are restricted to like low weight poly. For example, the Fourier codes they use 4 weight for different x. Okay. And if you try to use harder codes, then you need to do 6x, which is experimentally hard compared to 4x. So this is a Google at 2000 published on Nature at 2023 that they are actually using this service code, try to build this square lattice, and they can show that they really see that if they increase the number of qubits and the number of the qubits, I think it's 25 times 25, then and up to the 35, then they can see the error rate indeed the essence theoretically. So these are like very like new paper. I mean, quantum version is somehow like just recently been experiment. I mean, theory stuff almost at 20 or 30 years, but up to like 2 years ago, people started to see this service code indeed like suppress the errors. So I just want to say that if you believe this, then I will tell you that it's really cool. If you want to find out this in terms of this, okay, so I think nowadays that since there are many different like quantum corrections tests that there are different algorithms, but most of the most promising one that people believe is, or that Google I believe they believe is start using this superconductor and using this service code and scale and use this magic state distillation. Make the full tower code. But let's say, let me just, well, there are different counting methods, but let's say you have short codes. You want to do a short algorithm. So let's say you want to factorize like 1,000 bit of integer, then obviously you need 1,000 logical bits.
What was the formula again for the precision for sure?
I think that if you do like, if I remember, if you have like do n bit number, then you can, yeah, I think you need 10 like n qubit or something. Close, I think the older. If I think so,
Okay,
the standard RSA is like 0 like 1,000 bits, 2,000 bits. So you need like 1,000 logical bits. But if you want to use 35 times 35 service code, then each logical qubit need 1,000 service, 1,000 physical qubits. So you need like 30 times 30 with almost 1,000 physical qubits, so then you can go with one logical qubit. So but this is just some logical qubit. In order to have this so-called magic state distillation, I didn't detail, but you will need to put each service code. I mean, this is crazy. I mean, if you see you can imagine that in the Shor's algorithm, right? I mean, you can say that if remember that we have some quantum algorithm, we have some gates, right? Some gates. Then, if you do it experimentally, you need to imagine that these zero are not just a single zero, but a patch of a service code. And these are also a service code. These are service code. And when you try to do a gate, if this gate are Clifford group, you can do transversal. If it's not Clifford group, maybe some weird rotation, then you need to do this magic state. Need to have someone that prepare this distillation. And this distillation is not just distilled on a physical qubit, but a logical qubit. So you need a large factory of service code. So that you can do a magic state distillation. So you need to have a so-called T factor, which is a large factor you can keep doing distillation. So you need millions of physical qubits. So you can keep distilled. So that you will keep injection this weird state on the non-Clifford. And the issue of qubit. So issue of logical qubit will be a square. So it's a very heavy. So total physical qubit needed is it's maybe these numbers. I just yeah, these are some that you can check out the paper. But I think people believe that median of qubits, median of physical qubits, so that one can actually. So the problem comes from this T factor. You need median physical qubits to do this magic state distillation, much higher than the logical qubits. Okay, so these are just some probably so the idea is that in terms of doing Shor's algorithm, we need to do like 10 to the 10th quantum operations. But now the physical errors of these physical rates, basically is P, are for like very superconducting where they are like 10 to the -3. So this current error correction want to make this 10 to the -3 physical errors using QEC techniques. We do that 10 to the -. If it then yeah. So this is why very okay, so like service code plus register and QEC are the major quantum computing. Major people probably I'm not sure this is the best way, but people like to this is for quantum computing. And there are like other type of your qubits, they require less error corrections, but total topological qubits, and the existence of such qubits are still basically people are still debating. And yeah, so this is the final. Basically, the routes, the best route of what we did is service code plus hyperdecays plus maybe.
So just for reference, what is like the error rate for a classical computer for the bits?
If I notice, I think CMOS can do 10 to the -10. So CMOS, the error of CMOS is very 10 times is like 10 to the -10.
Oh, okay.
Yeah, very small. But for the quantum computing, since there, I don't know why, but in the low temperature, they only have 10 to the -10. So this is why we need like QEC.
Yeah.
We need this whole like bunch of large machinery. Oh, yeah, to finish this, just say some words. So there are actually much more like there are other kind of theoretical error correction codes, which is that's very beautiful, but probably cannot be implemented in the real world. You can check out this so-called low degree parity check code. This is somehow like technical. These are somehow mathematically that people try to like find the theoretical the most powerful theoretical error correction code. So let me explain. So in terms of this, if you see this QEC, right? If you see this as a service code, then you can see that. So this is NKD, right? So the best error correction codes should if I fix n, then I should make k to be as large as possible, right? Because this means that I use n physical qubit to encode k logical qubits. So the better code should be n is fixed and k large enough, d is large enough. So there's an idea for rate defined to be, let's say, k divided by n. So in terms of service code family, you can say there's a problem because now your rate is just 1 divided by L squared. So it becomes 0. Yes, L goes to infinity. Meaning that if you increase your size, then whatever size you get a lot of whatever L you make, you can only encode the constant physical qubit, constant logical qubit. So theoretically, that people try to find the code family of codes such that this rate k divided by n is constant, greater than 0. As n goes, so that and d also constant, greater than 0. So meaning that people try to find the codes that can achieve this very powerful like region, such that your k divided by n is a constant. It's much better than this. And in the classical error correction codes that people already find, but there's I think Tori code, right? So Tori code, the Tori code is like it's like around like just 20 years ago. And basically there's no theoretical breakthrough that passed like 10 to 20 years. And until that, so at that time people some people believe this quantum this condition, this quantum LDPC codes are not basically not exist. And but there's a breakthrough that in 2020 by a bunch of people that people finally some very theoretical guy, they finally some mathematician, they finally find a good quantum LDPC code. So basically there exists a family of quantum codes which rate is constant as n goes to infinity. So it's linear in n, so it's much more powerful. And the distance is also linear in n. So this is somehow like the so-called, this is why we call it LDPC. So constant rate linear distance. So but unfortunately, there are not, if you try to put into the experimental, it's not some 3-dimensional. It's not just like Torrico 2-dimensional. One can define as higher dimensional Torrico. You can imagine that if I have a cubic lattice, then I can put my X into maybe edges and Z into the face or the block or the volume. Okay, but this LDPC code is not something that you can push to the real 3D world. And many deep mathematics. If you're interested, you can check out LDPC code. And yeah, there are actually 3 architecture even by Microsoft Research. You can see if you want to know the so-called hypergraph, you can if you want to know how to construct this LDPC. And mathematically, you can prove that there exists such family, but how to derive this family exactly that story code. The people spend 20 years finally find this LDPC code, but LDPC code decoding and encoding are much difficult than this service code, and probably I'm not sure, but I believe that's hard to implement in your work. So just theoretical monster. So. Oh, by the way, these toricos are also connected to the condensed matter, so-called topological quantum field theory. If you're interested, you can check. There's a different way to build this torico. You can use this. You can build it as condensed matter. So there are some name. Yeah. So you can also ask what's the how to distinguish what's the physical meaning of this story. Start from physical perspective to understand this ground state of the torico. Yeah, so and you can basically so these codes, their graphs, they are so-called topological state. And why is called topological? Because you can see these graphs, they are robust. They are robust under the noise because they have very long length of this distance. So this is why they call topological, because they are somehow like robust to the local noise. And one can use this to explain a lot of weird phase in the condensed space. So topological phase of matter. If you want to, you can learn that. If you want to learn, you can try to learn yeah. So the perspective I talk about historical. I use this quantum information, this stabilizer formalism, but you can also understand using condensed matter. Yeah. Actually, these languages are. There's a dictionary that you can trace. Oh, okay. So this is I finished this version. Okay. So okay. So now I can talk about rest. Until the 30 minutes. So we can talk about some other interesting. Okay, so since we finished the error correction code, so now hopefully you'll believe that if you have this bunch of error corrections, then you can do the real quantum computing. Okay, so okay, so the rest of 30 minutes, let me start with another interesting unit.